Hello, everybody. I hope wherever you are in the world, you're having a good time and enjoying this course. We spent the last 3 sessions building our knowledge of Laplace transform, and it was only in the last session, which was by the way a synchronous session, that we used Laplace transform as a technique to solve a simple ODE. You can find the video of that session on Blackboard. Today in this lecture, we will continue using Laplace transform for solving ODEs, and I also explain to you the method of partial fraction expansion. Let me remind you that in terms of our course navigation chart, we are still in here. We learned how to drive a model for a process, and in case that it is a linear ODE, we are trying to use Laplace transform technique to solve that linear ODE analytically and obtain an analytical solution. Okay, let's continue the example of search tank. If you remember, the differential equation that describes the elevation of liquid inside the search tank was. In the previous session, we solved a simpler version of this equation in which inlet flow rate was 0. In this session, we will solve the more general form in which the inlet flow rate is there but it's constant. And if you remember in lecture number 5, we used the method of integrating factor to solve this equation and obtain the solution in the form of. But it took quite a bit of effort to use integrating factor method to obtain this solution. In this session, we will use the method of Laplace transform, and you'll see that it's going to be much easier. In the first step, we take the Laplace transform of the whole equation. And because Laplace transform is a linear operator, we can make this simpler. The Laplace transform of the first term is S HS minus small h at time 0. The Laplace transform of second term is, and in the third term we have the constant that is gonna be there as is, and then Laplace transform of 1 is 1 over s. And now I just need to rearrange this equation to obtain and from here we can obtain HS as and let me bring a portion of our reference table for Laplace transforms to here. So at this stage, we have to look into our table and find similar expressions to those we can see on the right hand side of equation. For the first term, I can see that if I play with that a little bit, I can make it similar to expression number 13. And for the second term, I can make it similar to expression number 6. All I need to do is to simplify the first term and multiply the numerator and denominator of the second term by tau. And now you can see that these two terms are exactly item number 13 and item number 6 of the table. So at this stage, we can take the inverse Laplace transform of the equation and convert it back to the time domain. The coefficient is constant, so it remains as is, and the inverse Laplace transform of the first term is this, and again we have a constant coefficient here which remains as is, and the inverse Laplace transform of the second term is this. And these two terms cancel out each other, so the solution of the ODE takes the form of, which is exactly the same as the solution that we obtained using integrating factor. Now let's see what steps we took to solve the ODE. Our first step was to take the Laplace transform of the ODE to convert it to an algebraic equation. Next, we solve the algebraic equation to obtain an expression for Hs. So this was our step 2. And finally, our last step was to take the inverse Laplace transform of Hs so we can map it back to the time domain and obtain the original function Ht. But solving ODEs is not always as simple as this case, and there are more steps involved. To explain that, I'll give you the next example. So in this example, we want to solve a second order linear differential equation, which is so we are not getting involved in driving this equation. We assume that this is an equation that describes a process in transient. But we know the initial condition of the system, which is at time 0, f is 1 and f prime at time 0 is 0. So our step 1 is still the same. We have to take the Laplace transform of the ODE. So I'll write the Laplace transform of each term separately first. And again, by referring to our table for Laplace transform, we can expand these terms. So the Laplace transform of the second derivative is s squared capital F of s minus s times original function at time 0 minus the derivative of original function at time 0. So these three terms correspond to the first term. Then we have 5 times Laplace transform of the first derivative of the function, which is s capital F of s minus function original function at time 0. So these are the second term plus 4 times Laplace transform of ft, which is capital Fs. So this is this term, and Laplace transform of 0 is 0. Now we can substitute the value of the function and its derivative at time 0 based on our initial condition. So f0 is 1, f prime is 0 at time 0, and here also f0 is 1. So now I can factor fs and rearrange the equation to obtain. And finally, I can solve this algebraic equation to obtain an expression for capital Fs. So this is our step 2. By the way, if you refer to the textbook, the way it shows this solution is in the form of fs is equal to capital N of s, which stands for the numerator, and the denominator of the function is called capital D of s. It's just a notation, but I just wanted to bring it up so if you refer to the book, you understand what it means. Now our next step is to go back to our Laplace transform table and try to find an expression that matches our solution for fs. But we cannot find anything that exactly matches this rational function. That's why here we have one extra step. So in this extra step, first we try to factor the denominator of the function, which is s2 plus 5s plus 4. So we want to factor it and break it down to first degree polynomials. Sometimes I call them the elementary building blocks of this expression. And for that, we have to find the roots of this quadratic equation. And if you remember, I just give you a refresher in here. For a quadratic equation in the form of ax squared plus bx plus c equals to 0, we use the quadratic formula to obtain the roots, which is x is equal to minus b plus and minus square root of b squared minus 4ac divided by 2a. If we compare our quadratic equation, in this case a is 1, b is 5, and c is 4. So the roots of this equation will be s equals to minus 5 plus and minus a square root of 5 to the power of 2 minus 4 times 1 times 4 divided by 2 times 1. And if I simplify this, it will be minus pi plus and minus. Within the square root we have 25 minus 16, which is 9 divided by 2. And from here we will get two roots for the equation. S1, which is minus 5 plus 3, which is minus 2 over 2 or minus 1, and S2, which is minus 5 minus 3 or minus 8 divided by 2, which is minus 4. So it means that we can write this second degree polynomial in terms of its elementary building blocks, which are s minus its first root, which is negative 1 or plus 1, times s negative 4 or plus 4. So this is equivalent to the denominator of our expression. So this is capital D of s. And here I believe I had a mistake. So this is supposed to be capital D of s. Okay, so we just plug this back in our expression and we get fs is now equal to but we are still not done because we cannot still find a similar expression in the table. For that, what we have to do is we have to split this rational function into two terms. But unfortunately, we don't know the numerators of these two rational functions. So we just call them alpha 1 and alpha 2. And we have to find proper alpha 1 and alpha 2 that gives us the exact expression that we have on the left hand side. And this is where we need the method of partial fraction expansion or partial fraction decomposition. And this is quite simple. To find alpha 1, all we do, and let me call this left hand side. So this is technically the left hand side of this expression. To find alpha 1, we have to multiply the left hand side of the equation by the denominator that corresponds to alpha 1. So in this case, it is s plus 1. So if we do the multiplication, s plus 1 will be cancelled out from the denominator of this rational function. So we will have s plus 5 divided by s plus 4. And what we do is we evaluate this at the root that is corresponding to s plus 1, which is s equals to minus 1. So if I put s equals to minus 1, I will have minus 1 plus 5 is 4 divided by minus 1 plus 4, which is 3. So our alpha 1 is 4 over 3. In the same manner, we can calculate alpha 2, which is the left hand side of the equation, multiplied by the denominator, which is corresponding to alpha 2, s plus 4. So we get s plus 5 divided by s plus 1 in this case, and we evaluate it as at s equals to minus 4. So we get minus 4 plus 5 or 1 over minus 4 plus 1 or minus 3. So this is our alpha 2. So now all we need to do is just substitute alpha 1 and alpha 2 in the expression that we got for fs. So fs will be 4 over 3 times 1 over s plus 1 minus 1 over 3 times 1 over s plus 4. So this whole process up to here is a step 3. And now our step 4 is just inverting the expression from the s domain back to the t domain by taking the inverse Laplace transform. So we can refer to our table and see if we can find anything similar to these two terms. So I just checked the table and found that expression number 5 is an exact match. So I just copied that. I'm gonna put it here. So if we follow this expression, the inverse Laplace transform of 1 over s plus b is e to the power of minus bt. So we can simply find ft, which is 4 over 3 times e to the power of minus t minus 1 over 3 times e to the power of minus 40. And this will be the solution of the second order linear ordinary equation.